And let's look at a couple more examples of absolute value equations. So here we have the absolute value of 4x plus 3 plus 2 equals 0. All right, now to use this property of the absolute values, we've got an absolute value equal to a number. We can split that into two equations. The part under the absolute value equal to c, and the part under the absolute value equal to the opposite of c. We need to have the absolute value by itself, and we don't have that here. Right, we've got the absolute value plus a 2 equal to 0. So we need to get the absolute value by itself, and that means we'll need to subtract 2. So 4x plus 3 equals negative 2. Okay. Now, we could apply this procedure, except that we might want to notice something about this equation. We have the absolute value of 4x plus 3 equal to a negative number. Now, recall what the absolute value represents. It's saying the distance from 0. Distance from zeros can never be negative. Right? So absolute values are always greater than or equal to 0. So we know right away that there's no solution. To this equation. It's a contradiction. If you did not do this, you could still, or notice this, you could still go through this procedure, but then, as I've said before, you need to check for extraneous solutions. Both of the solutions you get from this, when you plug them back into the original, will not solve it, because nothing plugged into this absolute value will give you negative 2. To add to the 2 to get 0. Right? So there's no solution here. All right, let's look at another example. This particular equation has two absolute value expressions. Absolute value of x minus 3, and then this is subtracted with the absolute value of x plus 7, saying that equals 0. Okay, well, we'll want to proceed the same way. We want to isolate an absolute value, and so we'll do that. We can add this absolute value of x plus 7 to both sides. It gives us x minus 3 absolute value equals absolute value of x plus 7. All right. So this x plus 3 and x plus 7, right, the distance from 0 for both of these is equal. That's what this this equation is saying. Right? And so it could be the case that x minus 3 could be equal to x plus 7. That would satisfy this equation, right? If the values of them are equal, then their absolute values are going to be equal. Okay? Or one of them can be equal to the opposite of the other, because if this were the opposite of x minus 3, so x plus 7 is the opposite of x minus 3, their absolute values would be equal. It's the same reason that negative 2 equals 2, right? They're opposites, but we're taking the absolute value of one of them. So if I put the absolute values here, we'd have kind of the same situation. If this were the case, right, 2 and negative 2, they're not equal, but their absolute values are equal, right? So we just need to choose one of them and take its opposite. Doesn't matter which one. So x minus 3 equals opposite of x plus 7. All right. So very similar to how we handle a single absolute value, we just drop them and then change the sign on one side. Okay, let's solve these. So for this first one, subtract the x, we get negative 3 equals 7. Okay, well that's false. And that means there's no solution from this side. Okay, let's try the other side. We have x minus 3 equals negative x minus 7. We're going to distribute that negative to the x and then into the 7. And then we'll add the x, add the 3. We get 2x equals negative 4. Divide by 2, x equals negative 2. All right. So let's check that in the original. So we'll have absolute value of negative 2 minus 3 minus absolute value of negative 2 plus 7 is 0. So we have absolute value of negative 5 minus absolute value of 5 equals 0. Well, absolute value of negative 5 is 5, minus absolute value of 5 is 5. 5 minus 5 is 0. So this is indeed a solution, and that would be part of the solution set, negative 2.